When we have vectors in a plane, it's important to be able to draw them properly and to be able to add and subtract them, multiply them by scalars, and divide them by scalars, which is pretty much the same thing. In this video, I'm going to give you the information for subtracting and for multiplying by a scalar, but we're not actually going to see examples of that because you can intuit that from the remaining information. And I like to leave a few things up to you to do, so you'll have to figure that out a bit on your own, and we'll go over it if you have some difficulties in the problems that come after. We've earlier defined a vector, and we've had a statement that tells us how it's drawn on a graph. Now we're going to take a look and see what these things mean and how we can use them. If we were using a number line, going back a long ways in your mathematical education, then if we were adding something like 4 and 3, we would simply just start at the origin, and we would move 4 units to the right, since it's a positive direction, and then 3 additional units. We'd look down, see that we're at the 7, and then we'd say that's our answer. We've gone 7 units. With vectors, it's just as simple. In this case, you have a vector that's 4 units long, so we draw it, and we have a vector that's 3 units long, so we draw that. They're both to the right since they're positive vectors. To add them, we place them tip to tail in line. So we have the tail, tip, tail, tip. We never want to have 2 tips together until you're very, very good with subtraction and you're okay with doing that geometrically. But for addition, certainly never have 2 tips together, okay, or 2 tails together. And the resultant vector here, the one that you get after you add them together, is a new vector that goes from the beginning of the first to the end of the second. If you had more vectors, you would go from the beginning of the first to the end of the last vector. We can do subtraction on a number line the same way. And the subtraction with vectors is much the same idea. So we go 4 this way, and then we go 3 back because we're subtracting. Okay. Notice how I've written it here. I wrote 4 plus a negative 3. I didn't write 4 subtract 3 because vector subtraction isn't exactly defined with a subtract symbol here. We'll see what to do in just a second. So we would draw out the vectors. We have 4 this way, and then we have a negative 3, so it comes back 3 in the opposite direction, and that gives us 1 for our resultant. So we start at the first vector, and we extend along until we get to the end of the last vector. So it would go just like this one. Now remember, these are supposed to be over top of each other. They're just not over top of each other because it would be difficult to see them that way. You don't want to try and draw your vector like this on an angle. That wouldn't make any sense at all. These are both along the x-axis, okay, or the horizontal axis. The result is called the resultant, no matter how many vectors are summed. If you compare the negative 3 to a positive 3, you get the length that you need for subtracting vectors of any type, okay, or of any direction rather. The negative makes it go the opposite direction. So if I was doing 4 subtract 3, if this was a subtraction, this was a positive 3, so there was 4 subtract 3, then I would reverse it so it looked like this. So I'd take the second vector and I would flip it around by just reversing its direction. I'd take it would look like a positive 3, and I'd just reverse it so I put the arrowhead on the opposite end. And then I would add that new vector with my original one. That's all you have to do. It's quite straightforward. But sometimes it gets a little bit conceptually difficult at first, so it will take a little bit of practice for many of you. Now in this case, we've got vectors that are perpendicular to each other. We have 4 units right, and we have 3 units up. Both of these are considered positive vectors, and up is a positive direction, and right is a positive direction, but they're not along the same axes. They're along the x and the y, or the horizontal and the vertical, whatever you want to call them. To add these vectors, we have to do the tip to tail method just like we did before, though, so we just follow the same steps. We start with the first vector, and then we put the tail of the second one with the tip of the first one, and we continue along. It's like traveling along. Imagine you're walking along. You can't go if the 2 tips are together, because where would you go? It tells you which direction to go. You have to go this way. So you go 4, and then you go 3, and that's where you end up. You start here, and you end up here. Now, you could do the reverse. You could start with the 3, go up, and then go up to 4. If you put the resultant vector in, it would start from here and go to the finish. the shortest distance between here and here, straight line, finish the triangle. In each case, you'll see that it's the same vector, okay? It might look like it's in a different location. The location doesn't actually matter as long as they're parallel, but it's even in the same location in this case, and they're pointing in the same direction. If I use trigonometry or my protractor, I can calculate this angle or measure the angle, and it'll give me the same location. Okay, this will be the complement with this one. Okay, so the resultant is a vector, so it has to have both magnitude and direction. All vectors have to have that, or you haven't completely answered the question. If we carefully drew the original vectors to scale, we could use a ruler and we could measure the length. That would give us the magnitude, and we could use a protractor and measure the angle. But once we have the angle like that, I think I skipped something. Okay, well, we won't be done once we have the angle like that. I didn't skip, I tried to skip ahead, but we'll do this first. Using trigonometry, that's another way to get the length and the angle. We can use Pythagoras' theorem to get the length of the hypotenuse since it's a right angle triangle. If it wasn't a right angle triangle, that doesn't foil us with trigonometry because, of course, we can just use non-right angle trigonometry, which is only slightly more complicated. The angles in a right angle triangle can be found using the inverse trig ratios, so that makes it nice and simple. Now, to find this angle here, you would use the inverse tangent of 3 over 4, because that's the TOA from SOHCAHTOA. It's important to try to use, as often as you can, quantities that are given to you to begin with. You shouldn't use the calculated hypotenuse in this case, unless you can, if you're very confident. There's nothing wrong with it conceptually. But the reason you don't is because what if you made an error there, then the rest of your stuff would all be wrong too. Plus, if this was an experimental situation and you knew these very precisely, they were manufactured or to some degree, so you knew these vectors quite well, then you would want to use those more than something that you determined during the experiment. It's as often as possible. Now, what I was starting to get to earlier, it was slightly ahead of schedule, was that trigonometry gives you the numbers for the angles, but it doesn't really tell you where the angle lies in three-dimensional space or even two-dimensional space. So you have to do something to tell your reader, or the person you're talking to, where that angle is. There's 3 different options. You can give the angle relative to a reference point. For example, you could say a boat traveling across a river is going at 4 meters per second at 30 degrees to the current. I've put the per second in this case in the way that I personally prefer, but the IB likes it this way. Now my degree symbol is out of place, so I'll just put that back. There we go. Just lock that back up. Okay. You can also use an angle relative to the cardinal bearings. We tend to put the north or south first and the east or west second. But, sometimes myself I even reverse that, but you should be putting the north or south first and the east or west second officially. So the 37 degrees tells you how far to rotate down from north towards the west direction. A bearing is also acceptable. You can go from 0 to 360 degrees and give a proper bearing. Our resultant was drawn as so. 3 and 4 makes a nice easy triangle, so for quick examples, it's nice to use these numbers, because we just get 5 for the R. It's a 3, 4, 5 triangle. If we choose to use angle theta, which would be right here in this corner, if I put a theta there, we would have the 3 over 4 that we talked about before. This gives us 37 degrees if we take the inverse tan. The resultant is 5 units at 37 degrees above the horizontal is a fine way to answer the question. You can also say the resultant is 5 units at north 53 degrees east if you take the one relative to the vertical, or you could also use that angle for a bearing. Vectors can be added. I already moved these out of the way for you. Vectors can be added if they're of the same type, but not if they're not of the same type. So a force vector and a displacement vector, you can't add those together. It's like apples and oranges. They have to be the same type of vector to add them together. If it's not a displacement vector, then they also have to occur simultaneously. Displacement's okay because it's independent time. You can walk for a while, stop, and then walk for a while again. It doesn't really matter. But simultaneous vectors have to be the case for things like velocity and force, because otherwise the vector addition doesn't work properly. Here's a quick example. Adding displacement vectors to find average velocity. A hiker walks 3 kilometers per hour east for 1 hour and then walks 2 kilometers per hour south for 2 hours. So we're just going east and then south to make a nice right angle triangle. What is the hiker's displacement is the first question. To get displacement, we just follow our triangle. So the 3 brought us here, and then the 4 brings us to here. The displacement is from the original starting location to where the person ends up. So she goes along here. That's the displacement. She should actually travel that way, but that's still her displacement. So we do Pythagoras' theorem, we get our 5. This is another 3-4 triangle, so it's 5 kilometers. This time the theta ends up being 53 degrees the way we would normally calculate it, 4 over 3. But it's down here, we have to give a proper location for it, so you can use 143 degrees as a bearing. You can go south 37 degrees east, or if you want to reverse the east and the south, that's not too big a crime, but it's preferable to do it this way. This distance is completely different than displacement in this case. The distance is where she actually walked. She didn't go along the hypotenuse of that triangle. She went 4 and then 3. She did the components. Okay. The average velocity is displacement over time. So once we have the displacement and the distance, we can do average velocity. We can also do average speed. Average velocity is the displacement, so it's 5 kilometers, and we have a direction divided by 3. The 3 doesn't affect the direction, so we just get the same direction in the end. The average speed, it's not displacement anymore, it's distance. It's not even the magnitude of the average velocity. That is not the average speed. The average speed is a different animal altogether. So without having a marker to indicate it's a vector, it's the average speed. It's distance over time, 7 over 3 in this case, which is 2.3 kilometers per hour. Okay. Now, if you were multiplying a vector by a scalar, this example doesn't show that, but it's quite simple to imagine because the word scalar sounds a lot like scale, and that's exactly what you're doing when you multiply a vector by a scalar. You're scaling it by the amount that you multiply by. So if you multiply a vector by 2, if I took the displacement vector and I multiplied it by 2, I'd just get 10 kilometers at the same direction. So it's just scaling the length. It makes the length either longer or shorter depending on whether or not you scale by a number greater than or less than 1. Okay. That's all there is to multiplying by a scalar. You can divide by a scalar as well as we did here, no problem, because dividing by a scalar is just like multiplying by its reciprocal, so it doesn't matter. You just do it, and it doesn't affect the direction at all.